All right, my name is Denis Cormier. I'm a professor at Rochester Institute of Technology, and I'll give a talk here on metal droplet jetting, molten metals. And I always enjoy coming to TechBlick to see things that I've never seen before. And so for at least a handful of you, I hope this is new. And if you have seen this before, hopefully there's some new aspects that you'll see that we've been working on that you hadn't seen before. Some of the motivation here. So we use all the same digital printing processes that all of you use every day. We do aerosol jet printing, micro dispensing, inkjet, photonic curing, et cetera. We use those for projects every day. What I'm talking about here is not intended to replace them. It's just a different tool in the toolbox for different applications. And so a big part of the motivation here recently, well, within the last year, is there's a company called Impossible Objects that makes a very high-speed carbon fiber composite additive manufacturing process. And this is their first high-speed installation, which is in our lab about 3 months ago. So that's the machine running. That was one of the installation test prints that you see running right there. So it's a CBAM 25 machine. It's printing 25 sheets, half-meter square sheets of carbon fiber per minute right now. It will get up to much higher printing speeds in the future. We've been doing a lot of funded work with them. And some of the questions got into, could we do power distribution lines, things like that, and embed them in the 3D structure? And those require high currents. We didn't want the traces to heat up and risk structural damage to the composite, the drone, that sort of thing. So that's when we started looking at, can we print solid core copper, specifically copper lines? So this was a separate process that we've been working on. We bought the very first machine that was ever built, commercially available machine with this, and the two videos in the top here show what it's doing from both the droplet ejection and what happens downstream. So the way the process works, we have metal wire or rod, feed it into a little micro crucible where it melts, and then on demand eject droplets, molten metal droplets onto a moving substrate. So this machine was originally intended for metal additive manufacturing, not printed electronics. So that's a video of the machine in our lab printing a cone-shaped structure, and that's what it looks like in real time, moving around. It was designed to print aluminum parts, not copper or silver printed electronics. But a couple of years ago, we started tinkering and toying with, can we print aluminum traces at least to get started? And one of the really nice things is once the droplets land, it's molten metal that solidifies. There are no nanoparticles that have to get dried or cured or anything like that. So what do we need to do to go from aluminum 3D parts to copper or silver printed electronic traces? Obviously, there's the software part of it. We're not slicing STL files and printing layers. We're printing traces from Gerber or other types of electronic circuit files. We'd like, for materials, we want to go from aluminum to copper or silver. Print parameter optimization, the line quality is extremely important for certain applications. So I'll talk just briefly about each one of these things. And then obviously for power distribution, high currents and things like that, we have to have really, really good conductivity. So we're seeking to match bulk conductivity of copper. And then we get into the production economics. I'm an academic, most of you are not. We need this to work in the real world. So the cost of the raw materials, but also is the process fast enough to be useful in the real world? The last one is not one that we had on there originally, which is substrate compatibility. That's something that I'll talk about at the very end. And that's